Black holes eat, not like you imagine, not slow, not clean. We are talking about cosmic feeding frenzies that break every rule we thought existed. 40 times the theoretical limit. Stars ripped to shreds in 50 days. Entire accretion disks destroyed and rebuilt in months. Jets that stretch distances we cannot even comprehend. The universe has monsters at its core, and they feast in ways that challenge everything physics said was possible. You know the image, the glowing disk, the artistic rendition with elegant spirals. Throw that away. Real black hole feeding looks nothing like the poster. It is violence. It is chaos. Some black holes consume the mass of our entire sun every single day. Others tear through stars like tissue paper. A few break their own accretion disks into pieces and devour them separately. The mechanisms are different. The scales are different. But the outcome is always the same. Mass goes in, light explodes out, and we are just starting to understand how many different ways this can happen. This script is researched and factual, using sources from Nowhere Lab published November 2024 on super Eddington accretion, discovered via JWST observations, Nature Astronomy volume, published October 2024, confirming LID 568 feeding at 40 times the Eddington limit, and physics published December 2024, analyzing the mechanisms behind extreme accretion rates. These are not general astronomy websites. These are peer-reviewed observations from the James Webb Space Telescope and Chandra X-ray Observatory, documenting events we thought were impossible. Now back to the information. November 4th, 2024. Nowhere Lab astronomers using JWST and Chandra make the announcement. This black hole is feeding at a rate 40 times faster than the Eddington limit. The what? The Eddington limit. The theoretical maximum a black hole can eat before its own radiation pushes food away. Picture it this way. As matter falls toward a black hole, compression heats it. That heat radiates. That radiation pushes outward. At some point, the push equals the pull. Balance, the limit. Beyond that, a black hole theoretically chokes on its own light and stops growing. Except LID 568 does not care about theory. Not gentle winds, torrents. The speed and size tell a story. This is not gradual feeding. This is a single episode of rapid accretion. The black hole is gorging. 40 times past the limit physics said would stop it. How? The outflows act as a release valve. The excess energy gets vented. The system does not become unstable. It stays in this hyperfeeding state. The discovery changes the game. Supermassive black holes in the early universe grew so big so fast because they had feeding frenzies. Short bursts where they consumed absurd amounts of mass in geologically brief windows. LID 568 is caught mid-feast. The timescale matters. If this feeding episode lasts even a cosmologically short period, it explains how black holes reached billions of solar masses when the universe was still young. The powerful outflows observed suggest the event is temporary but impactful. A significant fraction of the black hole's mass growth happens in this single binge. The numerical simulations from Syracuse University and University of Leeds match the observations. Peak accretion timescales sit around 50 days for complete tidal disruption events, but this is different. This is sustained feeding beyond limits. The frozen-in approximation model fails. The CN22 model works. The data fit. LID 568 proves a black hole can exceed its Eddington limit and provides the first chance to study exactly how. The system is 1.5 billion years old measured from the Big Bang. The light took over 12 billion years to reach us. We see the early universe. We see black holes learning to eat. Closest tidal disruption event ever observed to date. MIT astronomers spot it February 2023. The galaxy sits quiet for years in archival data. Then, late 2014, brightness explodes. The flare peaks in 2015. By the time astronomers catch it, the event is already unfolding. This is not a normal feeding pattern. This is a black hole catching a star that wandered too close. The tidal radius, that critical distance where the black hole's gravity differential tears stellar material apart. Spaghettification, the technical term for something horrifying. One side of the star feels stronger pull than the other. The star stretches, it elongates, it rips into a stream. Traditional surveys missed it. NASA's NEOWISE mission scanning the entire sky in infrared caught the signature. The team traced the flash back, 42 megaparsecs from Earth. The source got brighter suddenly. Late 2014 marks the start. By 2015, high luminosity. Then the decline back to quiescence. The shape of the light curve tells the story, rapid rise. Gradual decline following a power law of time to the negative 5/3. Classic tidal disruption profile, but finding it in infrared opens new hunting grounds. How many tidal disruption events have we missed because we only looked in X-rays and optical? Martin Rees in 1988 described how half the disrupted material stays bound. The rest escapes, the bound material accretes, forms a luminous disk. The explosion of radiation reveals dormant black holes at galaxy centers. Rosat All-Sky survey in the early 1990s made the first detections. As of May 2024, roughly 100 tidal disruption events are known. NGC 7392 is number 100 something, but the closest yet. 1/4 the distance of the next nearest. Close means detailed observations. 3 X-ray telescopes watched it. NASA's Chandra X-ray Observatory, Swift Gamma Ray, Burst Explorer, ESA's XMM Newton. The object gets the designation SAS 14 Li. The All-Sky Automated Survey for Supernovae found it in optical in November 2014. The X-ray spectrum changes over time. Material gets very close to the black hole. Smallest possible stable orbit. The disk forms from stellar debris, long tail of material flung away. Wind blowing from the black hole captured in bluish-white spectral lines. Not moving fast enough to escape. Alternative explanation possible, gas following elliptical orbit, observed at maximum distance where it travels slowest. Either way, this is stellar material being consumed in real time. The black hole has mass estimated at a few million times the sun. Peak fallback rate effectively independent of the disrupted star's mass and age. Approximately 50 days for a sun-like star destroyed by a black hole the mass of Sagittarius A star. That is the black hole at the center of our Milky Way. 4.3 million solar masses, mostly dormant. But if a star wanders into its tidal radius, 50 days later, the feast peaks. The accretion rate, the rate stellar material falls back onto the supermassive black hole during the tidal disruption event, reveals signatures of both stars and black holes. Partial disruptions exist. The star passes near the supermassive black hole, loses outer layers, survives, continues in orbit, passes again, gets stripped again. January 2024. MIT team publishes discovery of 18 new tidal disruption events, doubles the number of known events in the local universe. ASSSN finds the candidates. Follow-up spectroscopy confirms. The team led by Megan Masterson at MIT's Kavli Institute makes a key finding. Tidal disruption events occur across a range of galaxies, not just post-starburst galaxies. Thick dust clouds do not stop them. If you looked up and saw a bunch of galaxies, the tidal disruption events would occur representatively in all of them. The frequency calculation shifts. Adding 18 new events to the previous count, estimates now say galaxies experience a tidal disruption event roughly once every 50,000 years. That matches theoretical predictions. No exotic physics required. The black hole gets another meal. Repetitive feeding. The spectrum shows this. The light curve shows this. 1% of tidal disruption events are relativistic. These launch astrophysical jets from the black hole shortly after the star destruction. The jet persists for several years before shutting off. As of 2023, only 4 tidal disruption events with jets have been observed. Most are non-relativistic. Outflows similar to Type IB and Ike supernovae energetics. But that 1% with jets, those are the monsters. Peak luminosity of tidal disruption events is proportional to the central black hole mass. Can approach or exceed the combined light from every star in the host galaxy, some of the brightest sources in the universe. And they happen when a star gets unlucky. Wrong place, wrong orbit. 50,000 years per galaxy means our Milky Way is overdue. We have not seen one here yet. Statistically, one could happen tomorrow. Compared accretion rate predictions across stellar masses and ages. Perform numerical hydrodynamical simulations of sun-like star disruption by supermassive black holes. The model agreed extremely well with simulations. Peak timescale of accretion rate in a tidal disruption event is insensitive to star properties, almost entirely determined by the supermassive black hole mass. Measure the rise time. You peer directly into the property of the black hole, holy grail of tidal disruption event physics, presented at the American Astronomical Society's 243rd meeting in New Orleans, January 11, 2024. The paper clarifies complete tidal disruption events cannot exceed month-long timescales. Disproves earlier beliefs. They explain long-duration light curves peaking and decaying on multiple-year spans. This is fast, brutal, and over quickly. The black hole devours the inner subdisk first. Debris from the outer subdisk cascades inward, fills the void. The cycle repeats. Scientists thought this took hundreds of years. The simulations show months. Lead author Nick Katz, graduate student in astronomy at Northwestern, explains. Classical accretion disk theory predicts slow evolution, but some quasars show drastic changes over timescales of months to years. The inner part of the disk, where most light comes from, gets destroyed, then replenished. Classical theory cannot explain this. The simulations can. Different angles, like wheels in a gyroscope. The tearing region is where the feeding frenzy begins. Competition between black hole rotation and disk friction and pressure. The black hole wins. Inner and outer disks collide. The outer disk shaves layers off the inner disk, pushes material inwards. The process happens surprisingly quickly, over months. The inner region of the accretion disk can totally disappear, really quickly, over months. The system stops being bright, and brightens again. The process repeats. Conventional theory has no way to explain why it disappears or how it refills so quickly. These simulations answer both questions. The spin becomes the primary driver of periodic fluctuations in luminosity. Gas swirls around the black hole owing to intense gravity, forms accretion disk, most efficient energy conversion mechanism in universe, emits light and plasma jets. When the black hole spins on its axis, the disk wobbles. This precessional motion was studied in less luminous accretion disks before. Unclear if the same happens in ultraluminous disks that emit strong radiation. The large-scale radiation, electromagnetic, hydrodynamic simulation proves for the first time the precessional motion of a tilted ultraluminous accretion disk is caused by black hole spin. The motion periodically changes the direction of jets and radiation emitted from the black hole. Periodic fluctuations in luminosity of ultraluminous accretion disks may be caused by this spin-induced precession. The paper connects spin to observation, direct link. Follow-up spectroscopy from comprehensive search across full SDSS footprint. Spectroscopically confirmed quasars from SDSS DR7 catalog. Primary selection requires large amplitude variability. Delta G greater than 1 magnitude. Delta R greater than half a magnitude. Anytime baseline from SDSS and Pan-STARRS, 1 surveys. Photometry from Catalina Sky Survey verifies behavior. Optical spectroscopy from William Herschel, MMT, Magellan, and Palomar telescopes confirms 17 new changing look quasars. Confirmation rate greater than 20%. Candidates at lower Eddington ratio relative to overall quasar population. Supports disk wind model for broadline region. Changing look quasar fraction increases from 10% to roughly half as continuum flux ratio between repeat spectra at 3420 angstroms increases from 1.5 to 6. Roughly 1,000 changing look active galactic nuclei discovered to date. Yang, McLeod, Sheng, Potts, Vilforth, Jin, Guo, Dong. Papers from 2018 through 2025. 3 mechanisms proposed. Tidal disruption events temporarily enhance accretion. Obscuration by intervening clouds changes line of sight. Intrinsic changes in accretion rate. The majority thought to be caused by intrinsic variations in accretion rate. Exact physical mechanism remains unclear. SDSSV data from Zelton and others published 2024 contains 67% changing look active galactic nuclei, showing dimming, and 33% showing brightening. Approximately equal numbers get brighter and change toward type 1 or get fainter and change toward type 2. SDSS J 1628 plus 4329 experienced dramatic dimming and rebrightening within months, potentially driven by variable obscuration. These specific mechanisms may not represent the general population, but illustrate the upper limit of rapid variability any comprehensive theory must explain. Zwicky Transient Facility. Light curves analyzed November 2024 show on-state and off-state changing look active galactic nuclei share similar variability patterns with overall population. Distinct from extremely variable quasars, type 1 and type 2 active galactic nuclei. Suggests on and off changing look active galactic nuclei are not simply equivalent to type 1 and type 2. Instead of genuine transitions between two types, they may inhabit a critical state where moderate fluctuations in accretion rate lead to temporary spectral changes. The system teeters on an edge. Small changes in feeding rate cause big changes in appearance. The black hole does not fundamentally change. At the rate it consumes, matter shifts. That shift changes everything we observe. Discovered early 1960s by rocket-borne X-ray detectors. Binary system containing supergiant star and stellar mass black hole, 15 plus or minus 1 solar masses, 9.7 IAB donor star. Distance between them only 0.2 astronomical units. About half the distance Mercury orbits from our Sun. The two orbit with X-ray variability every 5.6 days. One orbit, also every 300 days. Believed due to precession of jets, black hole sucks matter from companion. Matter swirls into accretion disk, makes inward journey until falling past event horizon. Accretion disk extremely hot, 10 million degrees Celsius, 18 million degrees Fahrenheit. Emits radiation across electromagnetic spectrum, gamma rays, X-rays, visible light, infrared, radio waves. Cygnus X1 also has jets shooting out perpendicular to disk from near event horizon, magnetic field suspected. Compact object, typically few to tens of solar masses. Approximately 200 low-mass X-ray binaries detected in Milky Way. 13 discovered in globular clusters. Chandra revealed them in many distant galaxies. Emit almost all radiation in X-rays, less than 1% in visible light. Brightest objects in X-ray sky, relatively faint and visible. High-mass X-ray binaries form from two stars of different mass orbiting each other. More massive evolves faster, reaches end of life first, few million years, becomes giant, loses outer layers to companion, explodes in supernova leaving neutron star or black hole, can disrupt binary system. If star that exploded was less massive than companion when it exploded, system remains intact, though orbits may be more eccentric. Loses outer layers onto neutron star or black hole. This is the high-mass X-ray binary phase. Material forms accretion disk around compact object. Heats up from friction. Heating combined with jets causes X-ray emission. Companion star eventually dies, leaving neutron star or black hole paired with white dwarf, or neutron star or black hole depending on initial masses. Cygnus X1 10,000 times more powerful than the Sun. Most powered by gravity caused by black hole. Observational signatures clear. Spectral properties, fast variability, quasi-periodic oscillations in X-ray flux, different accretion states, high soft state with thermal disk emission, low hard state with power law spectrum, intermediate states, state transitions studied extensively, the corona contracts and black hole transients, the accretion disk geometry changes. Lamppost model versus extended model. POGO plus balloon-borne polarimeter measured X-ray orientation. Reflected off accretion disk, extended corona model fits observations. Larger region of gas encompasses black hole entirely. Weaker gravitational influence, less bending of X-rays, less reflected light off disk. The geometry is solved, at least for Cygnus X1. January 2012. New X-ray source flares and rapidly brightens. 2.5 million light-years away, classified as ultraluminous X-ray source. Second ever seen in M31. Target of intense observing campaign, NASA's SWIFT, ESA's XMM Newton. Radio observatories on ground. Results yield first detection of radio-emitting jets from stellar mass black hole outside our galaxy. Ultraluminous X-ray source thought to be binary system containing black hole rapidly accreting gas from stellar companion. To account for brilliant high-energy output, gas must flow into black hole at rate very near theoretical maximum. Feeding frenzy astronomers do not yet fully understand. Gas spirals toward black hole, becomes compressed and heated, eventually reaches temperatures where it emits X-rays. Rate of matter ingested by black hole increases. X-ray brightness of gas increases. At some point, X-ray emission becomes so intense it pushes back on inflowing gas. Theoretically, caps further increase in black hole's accretion rate. The Eddington limit, again, named after Sir Arthur Eddington, British astrophysicist who first recognized similar cutoff to maximum luminosity of star. Black hole binaries in our galaxy that show accretion at Eddington limit exhibit powerful radio-emitting jets moving near speed of light. Little known about physical nature of these jets. Detecting them at all confirms ultraluminous X-ray source is accreting at limit, identifies it as stellar mass black hole. XMM Newton first detected the source. Dubbed XMMU J004243.6 plus 412519 after astronomical coordinates. January 15th, 2012, marks detection. Went into outburst, remained bright until late May, then returned to undetectable levels, short observing window. But enough. Follow-up X-ray observations with SWIFT, radio observations with Very Long Baseline Array and European VLBI network starting late January. By early February, jets confirmed. Emission detected from both sides of black hole, moving away from black hole in opposite directions. Expansion velocity measured, approximately 2/3 speed of light. Distance from black hole to jet emission points calculated, roughly 300 million kilometers. Light travel time measured. Jet launched within days of X-ray outburst starting. Tight connection between accretion and jet formation. Debate exists whether many ultraluminous X-ray sources represent intermediate mass black holes. Hundreds to thousands of solar masses, middleweight versions between stellar mass and supermassive? Or are they stellar mass black holes accreting at or above Eddington limit? M31 source argues for stellar mass. The jets argue for Eddington limit accretion. The physics matches known stellar mass black hole binaries. But the luminosity exceeds anything seen in our galaxy. Supercritically accreting stellar mass black holes as ultraluminous X-ray sources. Poutinen and others published 2007. The model works. Black hole spinning, accretion disk tilted, precession, outflows, jets, all the ingredients. The luminosity comes from geometry and accretion rate, not necessarily black hole mass. several dozen ultra-luminous X-ray sources known in nearby galaxies, each potentially a stellar mass black hole eating at extreme rates, each a laboratory for physics we cannot replicate on Earth, each a feeding frenzy caught in the act. Easier to move because small. In simulation, feeding frenzy truly begins in tearing region, where inner and outer subdisks split. Competition between rotation of black hole and friction and pressure inside disk. Black hole wins. Inner and outer disks collide into each other. Outer disk shaves off layers of inner disk, pushes material inwards. Classical accretion disk theory predicts disk evolves slowly. Quasars appear to drastically change over months to years. This variation so drastic, it looks like inner part of disk gets destroyed and replenished. Classical theory cannot explain drastic variation. Phenomena seen in simulations potentially could explain this. Quick brightening and dimming consistent with inner regions of disk being destroyed. How gas gets to black hole to feed it is central question in accretion disk physics. If disk can tear itself apart and rebuild, that changes the entire picture. The violence is internal. The disk destroys itself. The black hole just waits. The tearing happens at the radius where black hole influence overwhelms disk pressure. That radius changes with black hole spin and disk properties. Needful physics, magnetic fields threading disk, turbulence from magnetorotational instability, radiation pressure from heated plasma, space-time warping from black hole spin, all interacting simultaneously. The simulations take weeks to months of supercomputer time for single system, but they reveal truth. The disk is not stable, not smooth. It fragments. It tears. It feeds the black hole in gulps, not steady streams. The variability we observe in quasars and active galactic nuclei reflects the disk's internal violence. The brightening and dimming cycles match disk destruction and reformation timescales. Months to years, fast by cosmic standards. Geological instant, but long enough to observe, long enough to catch systems mid-cycle. Changing look active galactic nuclei may be catching this process. The on-state when inner disk present and feeding. The off-state when inner disk destroyed and outer disk refilling the gap. The transition happening right now in galaxies we watch. February 2024. Astronomers discovered distant black hole that masters overindulgence. So far from Earth, light takes 12 billion years to reach us. Visible almost at dawn of time. Supermassive black hole with mass between 17 billion and 19 billion times the Sun. Power's brightest quasar ever seen by humanity. Maintaining emission requires black hole consume equivalent of Sun's mass in gas and dust every single day. Every day, one Sun consumed, the fastest growing black hole known to date. To achieve that luminosity, accretion rate must be phenomenal. The mechanisms must work differently than we thought. Standard models break down, slim disk models proposed, Abramowitz, Wang, and others, applicable to sources accreting at or above Eddington limit, show signatures of strong outflows even in low ionization emitting regions. Rodriguez Ardila published 2024 on ESO 138G001. Shows details of central part with nucleus, extreme physical conditions, super Eddington accretion in quasars, discussed by Marziani and Panda, published January 2025 in Universe Journal. Photometric reverberation mapping technique demonstrated by Pozo Nunez, published January 2025. Maps accretion disk beyond cosmic noon for first time. QSO J0455-4216 at redshift 2.662. 6-month campaign. Recovered delay spectrum followed expectations of Shakura Sunyaev. Thin disk, irradiated in lamppost geometry. Mean emissivity radius calculated. Method proves modest aperture facilities can deliver robust results. Accretion disk sizes measured. Black hole masses estimated. Scaling relations between accretion disk and broadline region sizes calibrated. With aid of quasars, bridging gap between local and early universe cosmological probes. Help clarify Hubble tension, aggregate reverberation mapping active galactic nuclei with other cosmological probes. Type 1 supernovae. Chronometric measurements, baryon acoustic oscillation data, quasar angular sizes, H2 starburst galaxies, Amati correlated gamma ray burst data. Getting Hubble constant directly from active galactic nuclei alone needs standard candles or rulers. Sizes of accretion disks allow characterizing angular sizes of active galactic nuclei in conjunction with redshift-independent luminosity distances. The Eddington breaker population represents the upper end of feeding rates, the most extreme examples. But the distribution is continuous. Many black holes feed at 90% Eddington, 80%, 50%. The super Eddington cases sit at tail of distribution, statistical outliers that reveal physics at extremes. Studying them teaches us what happens when systems push limits. Where do models break? When does radiation pressure fail to halt accretion? How do outflows vent excess energy? What role does black hole spin play? What about magnetic fields, disk thickness, inclination angle? All these factors matter. All these variables change the outcome. And we are just beginning to map the parameter space, just beginning to understand which combinations produce which behaviors. Black holes with accretion almost always produce jets under certain conditions. Relativistic outflows perpendicular to accretion disk, moving at significant fraction of light speed, some at 99% light speed. Where does energy come from? Two possibilities. Accretion disk itself, or black hole spin. Blandford-Znajek mechanism, proposed 1977. Jet energy extracted from spin energy of black hole via torque, provided by magnetic field lines threading event horizon or ergosphere. Model supported by general relativistic magneto-hydrodynamic simulations of accreting black holes. Magneto-hydrodynamic jets form spontaneously from generic initial conditions. McKinney published 2009. When accretion disks are thick, stronger jets and winds driven by either stronger turbulent magnetic fields or by large-scale fields advected from large radii. Evidence suggests black hole spin matters. M87 star, first black hole ever pictured. Event Horizon Telescope Collaboration, 2019, April 2019. Image shows shadow of supermassive black hole. Follow-up observations. 2024 reveal gamma-ray flare from M87 star. Jet of high-speed particles erupting at near light speed stretches. So far, emergence compared to blue whale erupting from single bacteria. Team leader Giacomo Principe at University of Trieste. Results offer first ever chance to identify point where particles causing flare are accelerated. Could potentially resolve long-standing debate about origin of cosmic rays from space detected on Earth. Black hole spin magnitude and direction. Small changes in these parameters produce large changes in jet power and morphology. Some systems produce powerful jets, others weak jets, some no jets at all. Why? The answer lies in the disk-jet connection, the symbiosis between accretion and ejection. Energy budget of jet fed by accretion process. Cosmic ray luminosity, limited by Eddington luminosity, multiplied by efficiency factor. What part of total energy budget goes into cosmic rays? X-ray binaries in Milky Way provide laboratories. Microquasars, stellar mass black holes with relativistic jets, SS433, quasi-persistent microquasar with supercritical accretion regime, 10 to 20 solar mass, compact object. High inclination, Eikenberry and others. Fabrica, 2004, detailed review. System shows jets, precession, variability. All the features of larger systems compressed into stellar mass scale. Time to the power of half proportional to square root of mass. Same processes taking hundreds of years in quasars take only minutes or hours in stellar mass black holes. Gravity adds speed to observations, allows studying accretion physics in real time. Human timescales, observable, measurable, comparable. Some feeding frenzies follow patterns, not random, periodic. OJ287. Binary supermassive black hole candidate. MOMO project presents latest multi-wavelength light curve, measurement of low primary supermassive black hole mass, approximately 100 million solar masses. The periodicity comes from orbital motion, two black holes orbiting each other, accretion disks around each, interaction between disks, tidal forces. Changing distances, all contributing to periodic signal. Single black hole with warped disk can produce quasi-periodic signals. Precession timescales depend on warp amplitude and disk properties. Can mimic binary signature. Galaxy mergers bring them together, but final parsec problem persists. How do they shrink from kiloparsec separations to merger? The feeding during and spiral changes. Accretion flows get disturbed, disks get truncated. Eccentric orbits produce time-variable accretion. The variability we observe encodes the binary properties. Some ultraluminous X-ray sources might be intermediate mass black holes accreting below Eddington, but stellar mass black holes accreting above Eddington can produce similar luminosities. Gravitational wave observations, changing picture. LIGO-Virgo-Cagra detections include black hole mergers in gap. GW1 90521, merger-produced remnant of approximately 150 solar masses. Unambiguous intermediate mass black hole. But formed through merger, not primordial, not grown through accretion. If intermediate mass black holes do exist and accrete, how do they feed? The feeding mechanics depend on mass and accretion rate. The gap in observations means gap in understanding. But the physics is the same, scaled by mass. The Keplerian orbital frequency scales as 1 over square root of mass. Same processes taking centuries and supermassive take seconds in stellar mass. allows direct comparison. X-ray binary and outburst maps to active galactic nucleus in flare. The analogy holds, tested repeatedly, confirmed by observations. Ruin published 2019 on analogous structure of accretion flows in supermassive and stellar mass black holes. The structure is similar, the geometry is similar, the spectral states are similar, the timing properties scale, factor of million in frequency matches, factor of million in mass. Black hole feeding from 10 solar masses to 10 billion solar masses follows same fundamental rules, same equations, same instabilities. Same mechanisms, just different time scales, different spatial scales, different luminosities. The feeding frenzy scales with the monster. The spectrum shape reveals accretion physics. Each tidal disruption event is experiment, no two events identical. Stellar masses differ, black hole masses differ, impact parameters differ, each produces unique signature, but underlying physics the same. Disk instabilities, thermal instability, viscous instability, magnetic instability, all proposed. Models predict cycles of decades to centuries. Observations show months to years, factor of 10 to 100 too fast. High-resolution simulations with full radiation transport needed. Long-duration monitoring campaigns needed. More changing-look active galactic nuclei needed. Bigger samples, better statistics. Lead 568 sits 1.5 billion years after Big Bang. Light left that galaxy 12 billion years ago. Black hole already has 7 million solar masses. Universe only 1.5 billion years old at that point. Super Eddington accretion explains it. Single feeding frenzy episodes, consuming 40 times Eddington for brief periods, gain huge amounts of mass quickly. Over cosmic time, the growth adds up. Need efficient mechanisms, need high accretion rates. LID 568 proves they happen. Proves black holes can break the limit. Now we search for more. JWST provides the tool, can find faint high redshift sources, can characterize them, can measure masses, can measure accretion rates. The next decade will reveal whether LID 568 is rare exception or common occurrence. Whether super Eddington feeding is niche behavior or standard growth mechanism. Researchers identified black hole in early universe appearing to accrete matter at 40 times standard limit. Universe filled with monstrous black holes dwelling in center of galaxies. Supermassive black holes millions to billions times size of sun. Some observed at great distances corresponding to epoch just 700 million years after Big Bang. How these black holes grew so large so quickly has puzzled astronomers. New observations of dim and dusty galaxy LID 568 with JWST show central black hole consuming large quantities of matter, overcoming limits set by outward push of radiation. While more observations needed, study indicates early black holes may undergo feeding frenzy of mass accretion, allowing them to reach supermassive size in short span of time. Haeun Seuss at International Gemini Observatory, Hawaii, and colleagues captured young black hole experiencing early growth spurt. Used JWST to study distant galaxy from epoch 1.5 billion years after Big Bang. LID 568 originally detected in X-rays by NASA's Chandra, but dust heavily obscures center, making nearly invisible in infrared until JWST. With JWST's incredible sensitivity in infrared finally able to uncover exotic object. From color and compactness, infer emission originates not from stars, but from accretion disk around central black hole weighing 7 million solar masses. Prototypical accretion disk is thin, swirling disk of matter circling black hole. As disk material falls into black hole, gravitational potential energy converted into heat. Heat radiates away, exerting outward push on material around black hole. Something interesting happens as more material falls in. Voracious black hole becomes more luminous. At some point, outward force of radiation overcomes inward pull of gravity. Luminosity where this happens, called Eddington limit, proportional to mass of black hole. Above this limit, material falling into black hole presumably blown away because of radiation pressure, shutting off accretion feeding the black hole. But LID 568 shows otherwise. Black hole feeding at 40 times Eddington. The discovery provides opportunity to observe how black holes exceed their theoretical feeding limit. Powerful outflows observed in LID 568 may act as release valve for excess energy generated by extreme accretion, preventing system from becoming too unstable. Discovery of super Eddington accreting black hole suggests significant portion of mass growth can occur during single episode of rapid feeding, regardless of whether black hole originated from light or heavy seed. Changes formation theories, changes growth timelines, changes everything we thought we knew. Tidal disruption events happen in all galaxy types, not just post-starburst. The frequency matches predictions, once per 50,000 years per galaxy. Milky Way overdue, Andromeda overdue. Every galaxy with central supermassive black hole is ticking clock. Next close stellar approach triggers next event. We watch, we wait, we catalog. Building census of how black holes feast when opportunity presents. Each detection refines models. Each observation tests theories. Each spectrum teaches physics. The violent beauty of tidal disruption. The ultimate expression of gravity's power. Star that survived billions of years. Evolved, fused elements, lived full stellar life. Then one bad orbit, wrong place, wrong time. Shredded in hours, consumed in weeks, forgotten in years. Except we caught it. We recorded it. We learned from it. The star's sacrifice was not in vain. Its death illuminated black hole feeding mechanisms. Its light taught us truth, that monsters eat, that feeding frenzies happen, that the universe is violent and beautiful and terrifying and magnificent all at once, and we are just beginning to understand.